The two most important factors in a PV system design are the loads and the yield of PV modules. In the previous video, you have learned how to carry out a load analysis. In this video, we shall focus on the yield of PV modules. Unlike the previous two simple design strategies, in this video we will discuss a detailed design approach to model the DC performance of the PV modules. For this detailed design approach, we will combine the different models and tools that we have discussed in preceding weeks. The design concepts that we discuss in this video can be used for both grid-connected and standalone PV systems. We will therefore use them again later in this course when we look into the detailed design strategies for different PV systems. The PV yield at the DC side, which is observed after the PV modules and before any subsequent power electronics, is the ratio between the instantaneous PV power generated by the PV power generated in the standard test conditions. Let's start by choosing a type of PV module for the system. The modules can be selected based on a variety of factors. The choice could be based on the type of PV technology, such as wafer-based or thin film, on the conversion efficiency, cost, or size of the module. Even the durability or the aesthetic appeal can influence the module selection. At the end of the design process, you can always pick a different type of PV module and reiterate the design process. PV system design is by nature an iterative process. We now have chosen a certain type of PV module. The next step is the detailed design approach, finding the DC energy yield of this module. At this stage of the design process, the calculations are carried out only for a single PV module, for which we will need the module area A. In order to find the DC yield, we have to apply an irradiance model and a temperature model. With the output from these two models, we can simulate the DC electricity yield and the other electrical parameters of the PV module. We'll first look at the irradiance model. As you might recall, the irradiance model consists of the solar position calculator and the optimizer model. The solar position calculator is used to determine the position of the sun in the sky for a certain location at fixed time intervals over a certain period of time. The time interval is an important parameter in the design process. With shorter time intervals, the accuracy of your system design is improved while your simulation time is increased. For large time intervals, the reverse effect is observed. Thus, a trade-off has to be achieved to have a good accuracy simulation in less possible computational time. Thus, as a general practice, a coherent time step of a 1 hour interval is chosen, which is an acceptable trade-off when performing full-year simulations. But one can also choose a different time interval, such as 10 minutes or a 1 minute interval, to improve the resolution of the time array and if the simulation time is not an issue. But once a time interval is fixed in the design step, it should remain the same throughout the design process to maintain consistency. The time period is usually chosen as a 1 year period. Next, the optimizer model is used to determine the optimum tilt angle and orientation of the PV module for that particular location. Both the direct and the diffuse irradiance components along with the albedo effects are taken into account. From this, the total irradiance incident on the surface of the PV module is calculated for every interval of time. This instantaneous irradiance is given by GM and is denoted in watt per square meter. Integrating the GM values over the full time period, which is generally 1 year, gives the annual incident energy density. Multiplying this energy density by the surface area of the PV module gives the amount of energy incident on the PV module in 1 year. This is denoted by EIM and is expressed in watt-hour per year. For the next step of the PV system design, we want to know the instantaneous operating temperature of the module. We therefore apply the temperature module, which uses the instantaneous irradiance calculated in the previous step as input. This model also requires the on-site wind speed and the ambient temperature, as well as the mounting configuration of the PV system. The data for the wind speed and ambient temperature can be obtained from a meteorological database or from a local weather station. Please note that meteorological data should have the same time interval as the input from the irradiance model. With this input, we can calculate the temperature of the PV module using one of the temperature models studied so far, the NOCT model, the Duffy-Beckman model, or the fluid dynamic model. With the data from the irradiance and the temperature models, we can go ahead and calculate the DC yield of the PV module. First, we should determine the maximum power point voltage, or VMPP. This is an important design parameter which is used later to correctly size the PV system. In order to determine the VMPP, we have to calculate the time-dependent open circuit voltage of the PV module. We can use this expression for instantaneous VOC, which combines the effect of the irradiance and the temperature. The temperature coefficient term KOC is a module-dependent property that can be obtained from the module datasheet. We can then determine the maximum power point voltage from the VOC in one or two ways. One method is to use a simple maximum power point technique, such as the constant voltage method, which offsets the open circuit voltage by a fractional value. The other method is an advanced technique where a MPPT algorithm is coded and simulated separately. In this video, we will use the first method for simplicity's sake. As such, we calculate the instantaneous VMPP by multiplying the instantaneous VOC by a factor of 0.75. The figure on the right shows the variation over the calculated VMPP over time. Note that the peaks and valleys seen here are caused due to the fluctuations in irradiance and temperature in the PV module. From the instantaneous VMPP, we can determine an average over the chosen time period. We can now finally determine the DC electricity yield of the PV module. To that end, we start with the calculation of the instantaneous efficiency using this equation. Such equation takes into account the effects of both the irradiance and temperature of the PV module. The temperature coefficient of the PV module is represented by the constant K. With the instantaneous efficiency, we can then obtain the instantaneous power output of the module PDC by multiplying the efficiency by module area and the corresponding instantaneous irradiance GM. Finally, the instantaneous DC yield, DCY, of the PV module is calculated dividing the instantaneous power PDC by the nominal power PSTC of the PV module. The above calculations of VMPP efficiency, DC power, and DC yield parameters are important steps in designing a PV system. These calculations will be used in later videos where you will learn the detailed design strategies for both grid-connected and standalone PV systems. In this video, you learned how to model the DC performance of the PV module. We combined the irradiance model and the temperature model to calculate the maximum power point voltage of the PV module. Moreover, we calculated the module efficiency, DC power, and DC yield. In the next video, we shall use this information to accurately design a grid-connected PV system.